The new chapter number 10, and the first topic is what is light or visible light. Write various view on it. Okay, the portion of wavefront 4000 angstrom, or rather we can say the portion of the wavelength which is lying between 4000 angstrom to 8000 angstrom in the electromagnetic spectrum is the visible light. The light itself is invisible, and with it things can be seen. You can see the objects with the help of light. Now, views on the light. First is the Newton's particle theory of light. Okay. The corpuscular theory of light set by Discrete in 1637 and derived Snell's law and explained the laws of reflection and refraction of light at surface that separate two mediums. This we have already studied, refraction and reflection of light. This model predicted that if the ray of light bends towards the normal, then the speed of light would be greater in the second medium. According to this theory, the speed of light is lower in rarer medium and higher in the denser medium. This theory of light was considered Newton's corpuscular theory. In this theory, light is considered to be composed of corpuscle. Okay. Now Huygens wave theory. In 1678, Huygens put the wave theory of light. This theory explained the phenomena of reflection and refraction, and it predicted that on refraction, if the wave bends towards the normal, then the speed of light would be less in the second medium, that is in a denser medium. This is in contradiction to the prediction made by using the other model. In 1850, Foucault carried out the experiment and predicted that the speed of light in water is less than the speed in the air. Now there is another theory of light. Describe a short theory history of the light. Okay, the wave theory was not accepted because the Newton's authority, and also because light could travel through vacuum, and a wave would always require a medium to propagate from one point to the other. But 1809, Thomas Young performed interference experiment and firmly established that light is a wave phenomenon. Since the wavelength of the visible light is much smaller than the dimensions of typical mirror and lenses, light can be assumed to be approximately traveling in the straight line. So in comparison to the wavelength, the distance traveled is large, okay, and it is assumed to be traveling in the straight line. The branch of optics in which one completely neglects the finiteness of the wavelength is called the geometrical optics. A ray is defined as the path of energy propagation in the limit of wavelength tending to zero. Many experiments were carried out involving the interference and diffraction of light waves. These experiments be satisfactorily explained. Thus, around the middle of 19th century, the wave theory seemed to be very well established. Now we shall talk about the wavefront and the types of it. When we drop a small stone on calm pool of water, waves spread out from the point of impact. This must have seen by all of you. Every point on the surface starts oscillating with time. Hence, at any instant, the surface would show circular rings on which the disturbance is maximum. All points on such a circle are oscillating in phase because they are at the same distance from the surface, or we can say from where the disturbance is generated. Okay, so all the points are at same distance from the point where the disturbance is produced. Such a locus of points which oscillate in phase is called the wavefront. So this is the definition of wavefront, is the locus on which all the particles are oscillating with the same phase. Okay, so the locus of the points which oscillate in phase is called the wavefront. Thus a wavefront is defined as the surface of constant phase. The speed with which the wavefront moves outward from the source is called the speed of the wave. The energy of the wave travels in direction perpendicular to the wavefront. So always the energy is traveling perpendicularly to the wavefront. Say for example, this is the circular wavefront which is shown here. Energy will travel perpendicular to the wavefront. Okay. Line perpendicular to the wavefront and indicating the direction of propagation of the wave is called the ray. So this is the ray. Hence the wavefront and ray are perpendicular. Okay. Next, if a point source emitting wave uniformly in all direction, then the locus of points which have the same amplitude and vibrate in the same phase are spheres which is known as spherical wave which is shown in this figure. At a large distance from the source, a small portion of the sphere can be considered as a plane. Our Earth is a sphere, but at a large distance we have a surface which is a plane surface. Okay, whatever surface which we are looking, say for example we look at the ground, then it is a plane surface. So this is known as the plane wave. Okay, at a large distance from the source, a small portion of the sphere will appear like a flat surface and it is known as the plane wave. It is shown in this figure B. Okay, this is the plane wave. Okay, wave fronts originating from linear source and propagating in three-dimensional homogeneous medium and isotropic medium. They are the cylindrical wavefronts. So this is the linear source by which the wave is produced and it is traveling in all the three dimensions. Okay, and it will have a cylindrical wavefront. Okay, as if a cylinder is expanding. For example, waves emerging from a tube light. Okay, which are shown in this figure number C. Now there is a use of wavefront to understand the wave propagation. The first is the principle: every point or particle of wavefront behave as an independent secondary source and emits by itself secondary spherical waves. Try to understand, if you have a wavefront, say for example this is the wavefront, then these points A prime, B prime, C prime, or you consider this wavefront, then the points are A, B, C. They will behave as an independent source of wave, or we can say these particles of wavefront behave as an independent secondary source and they will emit from itself the other secondary spherical waves. After a very small time interval, the surface tangential to all such secondary spherical wavelets are the points from waves are produced, give the position and shape of new wavefront. This is the principle, the basic principle. Okay, say for example you have this particular wavefront and these particles will produce the secondary waves. Okay, and these secondary waves will again travel, then again there will be a wavefront. These particles will behave as the secondary source of waves. Okay, and they will again produce the secondary waves. Now if you consider these wavelets means the particles on the wavefront, and if you just draw a tangential surface passing through it, then that tangential surface will give you the position and shape of the new wavefront. Basically, the Huygens principle is a geometric construction. Let us consider, suppose that f1, f2 represent a part of spherical wavefront at t is equal to 0. So this is your f1, f2 at t is equal to 0. okay, which is a wave propagating outward. So wave is propagating outward. Okay. Now, according to this principle, all points of this wavefront, that is F1, F2. This F1, F2 is the wavefront, and all the points, say the points are A, B, C, D, number of points are there. They will behave as a secondary source, and velocity of wave is, say, for example, V. Then distance covered by this wave in, say, time interval tau will be v into tau, because distance is velocity multiplied by time. So if you take time as tau, then v into tau will be the distance covered, and that distance is, this method is v into tau. Okay. Now spherical wavefront is shown here. The new wavefront is again shown, that is G1, G2. Okay. To determine the shape of wavefront at t is equal to tau, say for example you want to find the shape of this wavefront at t is equal to tau. Okay. Draw spheres of radius v into tau from each point on the spherical wavefront, and draw a common tangent to all these spheres then at time t after, say, time tau, which gives the position and shape of the new wavefront. So we just have to take the b as a, say for example, b as a what you call it, center of the circle. We have to take the radius is equal to v tau and draw the circular shape, or we can say draw a circle. Okay, and this way all the circles are drawn this way. Okay, now all these circles are there. Now these circles are having the points a prime, b prime, c prime on it. Now these points are then joined, and that will give you the shape of new wavefront. Okay, position also of the new wavefront, and that is denoted here as G1, G2. This is a spherical wavefront with center O. This is the center O, and again this is spherical wavefront. This was our initial spherical wavefront. Okay, and D1, D2 spherical wavefront is found backward. If you draw it in the backward direction, then you will have D1, D2 as a spherical wavefront. The points A prime, B prime, C prime on G1, G2 again will act as secondary source, and they will again start oscillating, and after, say, time t, again say tau time is taken, again you take the radius, or rather center, as b prime, a prime, c prime, and draw another wavefront this way. Okay, circles are drawn this way. Okay, by keeping the radius. Okay, and you will get the new wavefront in this direction. Say for example it is another wavefront, say e1, e2, whatever. Okay, now write Huygens principle and explain it. Principle already we have discussed in the last question. Every point or particle of wavefront behave as an independent secondary source and emit by itself secondary spherical waves after a very small time interval. The surface tangential to all such secondary spherical wavelets will give the position and shape of new wavefront. Okay, this is geometrical concept. F1, F2 we are taking as initial wavefront at t is equal to 0, okay, which is propagating outward. Now according to Huygens principle, okay, all points on the wavefront, that is already explained, say A, B, C, all these points are there, they will behave as a secondary source. Okay, and say for example at time tau, or after, say, time tau, if the speed of the wave is v, then v tau will be the distance traveled by this wave in this forward direction. Okay, to determine the shape of wavefront at t is equal to tau, what we have to do? We have to draw a sphere of radius v tau from each point on the spherical wavefront. So you draw a spherical surface, or we can say spherically surface shape. Okay, and what will it give? It will give the position and the shape of new wavefront on this G1, G2. Okay, this way you have to draw the circles. As such, in 2 dimensions, we take a circle as such they are the spheres. But in 2 dimension, if you want to understand, then what we have to do, we just have to take this A as a center and take V tau as a radius and draw a circle. That's all. And that circle will have different points which are A prime, B prime, C prime. Again, they will behave as secondary source. Okay, and they will again produce the new waves from it. Okay, so this will give you the wave front, or we can say shape and the position of new wave front after say time t, that is tau. If you want to again draw a new wave front, then again we have to take the centers as A prime, B prime, C prime. Okay, V tau will be the radius, and that will give you the new wave front. Okay, so this way this geometrical construction can be done and the new wave front can be drawn. Thank you very much.